Good afternoon, ladies and gentlemen. My name is Junda Chen. I'm a senior undergraduate working with Professor Alex Azarian in University of Urbana-Madison. And today I'm going to present a work and actually a very experimental project that I've been working on that is called LASEC VGT, which is a to be open source Julia package that over the 3 years we have been developed. So the initial of this project is that we have a bunch of undergraduates just rushing into our lab and then requiring the graduate student to mentor these students. And then we felt like we have repeatedly doing things like environment setup and teaching basic Julia and getting them to the basics of the research. And that actually takes a lot of time to mentor and a lot of time to invest. So to make these technology more friendly to beginner astrophysics or undergraduate students in their early career, while promoting our graduate students to work on the optimized code, we have designed this code base such that we want a package to be highly performant and also user-friendly so that undergraduate students can actually use this package as soon as they actually get it. And we actually abstract these problems into 6 layers. On the very bottom is what we call as OS, which is actually deal with the compatibility of different operating systems like Windows and Mac OS, so that when you actually download this package, you can install it in your desktop, and then there are actually many automatic scripts to actually guide you how to install it. And also, it actually scales to different you can actually deploy a Docker container so that it actually also runs in a cluster. And then we deal with efficient IOs in basically just HDF5 files, and then some magical type inferencing to dealing with the Julia type inference. And on top of that is the core library in which we have optimized our code for many, many years. And we adapt them to adjust for different kind of system and operating environment. And on top of that are the plot libraries, which we actually encapsulate many common plot functions. And also we have dynamic plotting and process monitor, such that a researcher can know like what's the progress of their work, et cetera, et cetera. Ultimately, this module we have tested and fine-tuned in many of our undergraduates and ourselves, and we actually work pretty hard for it. And then our performance actually shows that with our scalable system, we can have a relatively fine speed of execution for exploratory programming. If you have any question, I think I'll be out there in the poster session and happy to take any of them. Thank you.
Hi everyone, my name is Mike Foley. I'm a second-year grad student at Harvard, working with Alyssa Goodman and Lars Hernquist, and I'm going to be talking today about some recent work we've been doing looking at the development of turbulence in post-shock regions. Now, the reason I'm talking about this is because stars form in clouds of molecular gas, dense environments that are globally turbulent. Now, these clouds are quite large. We call them giant molecular clouds appropriately. But stars only form in small regions of it. And so we're talking about this global molecular environment that's turbulent. So we have a bunch of shocks ramming into each other on large scales. If we go down to the scales of star formation, recent studies have suggested that stars are forming in what we call these post-shock regions. So right around shocks or just behind shocks. And the reason we're looking at development of turbulence in these regions is because it's not necessarily a given that turbulence develops the same way behind a shock that it does on a sort of global environment for the cloud. And so if it does develop differently in these post-shock regions, then perhaps we have some additional considerations we need to look at for star formation. And so to do this, we've recently run 2 simulations. One is just looking at a single isolated shock, as shown in like the middle of this poster. And then we look at the second order velocity structure function, parallel and perpendicular to the shock, and also for the entire box. And we get very different structure functions for both the parallel and the perpendicular components. And then we also have driven a full 3D turbulent box, and we've been looking at the post-shock regions in this turbulent box, and we get a much different answer for the power law index for the second order velocity structure function than we do for the individual isolated shock. And so these are still very much preliminary, and I'm looking into like maybe other statistics to consider for this analysis. So I'd love to hear any input you may have if you've looked at problems related to this in other fields or used different statistics. But thank you very much. Posters outside. Love to talk to you.
So good afternoon, everyone. My name is Ali Esber. I come from France, and I work with a collaboration between three institute. It's between CAA. It's a Commissariat of Atomic and Alternative Commissariat of Alternative and Atomic Energy. The CSTB is the Science and Technique of Bâtiment Center, and the LOCI is the laboratory of my university. So the topic of my work is wind turbulence impact in ventilation engineering on buildings. So first of all, the problematic is to quantify the effect of the wind turbulence on the buildings. So to qualify the pressure distribution, as we see in this picture, when the wind hit the surface of and the sides of a building. So we have a distribution of pressure, and it's positive in the face side and negative on the other side due to the detachment of tourbillon and vortexes. And the main work is to see how this fluctuation will introduce inside the inlet and outlet of the ventilation system of any building or institute. So after this, we'll work about the influence of turbulence on global evaluation, because finally for the client, it's the more important is to talk about quality of the air, of the thought of the humidity and the energy consumption. And finally, the veracity of the quasi-static assumption, because it's assumption it's taken by the most of people that worked on wind turbulence. And we will prove that we cannot work on this quasi-static assumption, because there is a period when the wind, the turbulence enter in the building, there is a turbulence and frequency. We can see it before we attend the regime, the permanent regime. The PhD objective is, first of all, is make a study about the building length versus the turbulence, especially depending on wind typology and the roughness factor. It's the neighbor environment of this building that we study. To quantify this, the impact of the turbulence on the ventilation system, and identify all available spectrum. Here we are working now on the spectrum that can describe the turbulence in the wind, like Davenport or Van der Hoeven. And from this spectrum, we will generate the turbulence that will hit the side of building. But the main objective is to work about the orientation and the roughness of the entourage of the environment of surrounding. But if we have one problem, that with this spectrum, when it hits the building, we have more and more turbulence that will be generated depending on the shape of this building. So we work about into two sides. We will see it in the methodology of the study. And the first thing that we will study are also the vibration and the acoustic resonance. So now for the methodology, we divided our work into three parts. First of all, we have the theoretical approach that is based on the typology of the winds, the roughness factors, the turbulence and spectrum analysis, and the bibliographic study. The second one, it will be a nodal numerical approach. It's about the transfer of the air inside this building. Inside the building and the zone that we'll study, and we will use for that the Mattis modeling. It's a software or a motor developed by the CSTB to study this problem with a nodal numerical solution. And finally, we'll use wind tunnels. This is the wind tunnels of the STB, is one of the biggest wind tunnel in Europe, to also make experiment approach And there we will work also on the full-scale building in the CES site. And after that, we'll make a couple between the experimental study and what I will do like a simulation and generated by the spectrum, and then we will have like results that can be added to this spectrum to describe the real effect of the wind. The prospect is to validate Mattis in unsteady behavior, create a pressure database of the exterior surface that will be gathered from the experience in the wind tunnel, improve the designing step of in HVAC engineering, and we will identify other evaluation for that to participate a more resilient system. And briefly here, one of the simulations that we done, it's a parametric study. We will work with changing more parameters of the resistance of the conduct, the length and the diameter to get this thing. And I work on the equation of the energy equation, mass equation, to make one graph can generate all parameters at the same time. Thank you, and if you have your question, I will be outside.
Good afternoon. My name is Thomas. I'm from Heidelberg. I'm a student there at the Max Planck Institute for Astronomy, working with Hubert Klar. And we're focusing our work on turbulence and protoplanetary disks, especially in protoplanetary disk dead zones. And we're interested in turbulence in general in these disks because turbulence leads to the transport of angular momentum and therefore enables mass accretion onto the central star, which is shown here in this little cartoon. And secondly, because turbulence leads to the formation of flow structures like vortices, which then collect little dust grains and thus help us to form planets in these disks. In accretion disks, which are very well ionized, like around black holes, you have MHD turbulence caused by, for example, the magnetorotational instability. But the disks around young stars that we are working with are very cold, very dusty, and therefore very poorly ionized. And this means that this MHD turbulence cannot be present there. And this is why we are focusing on the study of purely hydrodynamic instabilities in these disks, where hydrodynamic means that the instability's occurrence only depends on the stratification of the disk in density and temperature, and on the local timescale of cooling or heating of the gas. And the work we've done so far could be split into two parts. The first part was the study of disk structure by use of a simple accretion disk model. From this structure calculations, we can then calculate the maps that you can see here. So we plot here where certain instabilities can exist in this disk. So we're, for example, looking on convective instabilities or shear-driven instabilities. And as you can see, most of these disks are, in fact, susceptible to these instabilities, which then leads to turbulence. And the second part of the work then focuses on the study of the resulting turbulence itself. So we're using the Pluto code here to simulate the gas motion in the disk, and we study how the turbulence then transports, for example, angular momentum and entropy in the disk. So here you can see a 2D simulation of this little fraction of the disk. And the instability which you see here is the vertical shear instability, and it can only exist where the disk can sufficiently fast cool. And this is why you see the structures emerging. So if you're interested in protoplanetary disks, planet formation, or astrophysics in general, please come talk to me, and we can discuss this at my poster. Thank you.
Hello, everyone. My name is Zerhan. I come from Nikta Fakhri's lab at MIT. And in my poster, I'm going to tell you a little story, a recent story about topological turbulence in biochemical waves. So the system that we're looking at is this biochemical waves that happens on the surface of a starfish egg cells. So it's a biological system that shows biochemical waves. And what is interesting about this biochemical waves is that if you look at the phase field and the phase velocity field of these waves, chemical concentration waves, you actually see signatures of of turbulence. And what I mean by that is that, so for example, if you look at the phase field of the biochemical waves, you see that there are this +1 and -1 topological charges. And if you look at the phase velocity field, which is basically just the gradient of the phase, what you see is that there are vortex dynamics that are constantly annihilating and creating and annihilating with each other. And what we found was that key statistics and scaling laws of this defect dynamics, so for example, the scaling laws of the velocities of these defects, as well as the area distributions of the vortices actually can be captured by the Onsaga theory of hydrodynamic turbulence, which suggests some interesting connections to, for example, the quantum superfluid turbulence and also turbulence of inactive fluid. If you're interested, please drop by my poster. And also, I want to mention that my co-authors, Jinghui and Pearson, will tell you more about this in their talks on Wednesday. Thank you.
Didn't get the memo about the slides. So I'm going to do it with that slide. So there is a poster out there, and I'll be happy to present it to you in the next few days. So from my understanding, we're all here because we share an interest in flow instabilities and turbulence. But we come from different backgrounds. So some people come from astrophysics and magnetohydrodynamics, some more hydrodynamic, and also complex fluids rheology. And the poster that I'm presenting kind of propose, I mean, it's talking about something, I'm more from the rheology community myself, and it's talking about viscoelastic instabilities and the interplay between elasticity and inertia. And one of the reasons why I think it can be of use to people outside of the rheology community is because in the last 15 years, some studies have shown that there are some parallel between some of the equations of magnetohydrodynamics in some regimes and what's going on in viscoelastic fluids. So you'll see this afternoon, I guess, with the talk of Mike Graham, that elasticity, so this elasticity for rheologists, usually it comes from polymers or stuff like that that are inside the fluids and that generate this elasticity. But for magnetohydrodynamic, it can come from the magnetic fields. But the idea is that this elasticity can alter the route to turbulence. And so instead of being just driven by inertia, like in regular hydrodynamics, you can also have purely elastic instability mechanisms. So also stuff like purely elastic turbulence, where inertia is not playing any role. And on the other end of the spectrum, when you have a little bit of elasticity, here the interesting thing that has been known for a while is that actually elasticity can stabilize some of the inertial instabilities. And so those two limits have been known for a while. And the poster that I'm presenting is kind of proposing a scaling for shear flows, curved shear flows, and a scaling that would cross over from the purely inertial scaling that have been known since Taylor and basically the beginning of the 20th century, and the purely elastic limit. And so it's kind of providing a proposal for how to go from one limit to the other and how to reconcile the fact that elasticity alone in the purely elastic limit can be driving the instabilities, or it can also be actually stabilizing in the more inertial limits. So if you want to know more about this and kind of muse on how it could be used outside of rheology, I'll be outside in the next few days. Thank you.
Thank you. It's a pleasure to be here. So let me just start with this. Nigel already introduced the subject, but one thing that, and I think you probably picked up on a lot of the excitement that's been going on in the area. Just to put this in perspective a little bit, Nigel mentioned this, but if you had gone to a meeting 11 years ago, and I was at a meeting 11 years ago in Cambridge in 2008, the view of how wall-bounded shear flows such as pipe flow and channel flows, how they become turbulent was very different than as we understand it now. It's not that the ideas weren't there, but we just didn't really, we had no successes huge arguments. There's a question whether even there was a finite critical point for any of these flows. It was just a lot of debate and a lot of non-understanding. And this has completely changed in the past 10 or 11 years. And Nigel gave you a good introduction to a lot of what's going on there. Let me just take you to this, which Nigel also showed. So this is what we know from Reynolds. We know that at low Reynolds number in a pipe, which is mostly what I'll talk about. Let's see if I can move this around. It's not so easy as I thought. OK, I won't use it. No, I'll be all right, thanks. Is that at low Reynolds numbers, you have laminar flow, as seen by the straight streak line. At high Reynolds numbers, you get turbulence very near the inlet of a pipe, and it continues down. And then in between, you have this interesting region where you have intermittent or transitional flow. And for a long time, it wasn't even known or understood that that is really deterministic Navier-Stokes dynamics. Those fluctuations were thought to be artifacts of this, that, and the other thing, and that would be a natural thing to assume. But we know that that's not true now. All right? So just to remind you of notation, I will use that word puff. One of these localized patches in a pipe is a puff, and I'll use that even if I didn't want to. I can't help myself. All right, so these are a variety of different shear flows, and they all show this intermittent transition. You see dark and light in here indicates turbulent and laminar flow. Just to give you some idea, you're looking often perpendicular to that. And this question was asked, and I want to just comment, and I don't have an answer to it, but these are all confined flows, and I do think that that is relevant. There isn't any one of these. A boundary layer does not appear on this diagram. Okay, I just want to mention that. And the scales are large. And I want to show you this. I'm going to show you a movie. This is actual hydrodynamic simulation done by Matt Chantry. Black is turbulent, white is laminar. So it's not just spatially intermittent, it's spatial temporal intermittent. And now we're going in logarithmic time. Now, I know that the name of this conference is Turbulence on Vast Scales. I'm sorry if I misquoted. And these aren't parsecs, but believe me, in this world, to go to systems that are 1,000 gaps by 1,000 gaps, we call that vast. It is just inconceivable from 10 years ago that we could reach these kind of scales. And the time scales, you have to do this for 10 to the 6 advective time units. And again, in this field, that is incredibly large. And that is what you have to get to the scaling regimes and answer the questions definitively. So this took a lot of effort, okay? That's not what I'm going to talk about. Nigel explained all this, and I don't have really anything to add. What I want to talk about is the physical mechanisms behind why you get this at all. Why do you have this transitional regime at all? And how does this drive things? That's what I want to get across, okay? And the key thing here is there's nonlinear fronts between turbulent and laminar dynamics, okay? So let's go back to this, and I just want to consider very quickly what happens at high Reynolds number, all right? The understanding of this goes back. It's classical. So let's look at what happens. You take a pipe, what an experimentalist would do if they're being careful, unlike, well, I don't want to say Reynolds wasn't careful, but you would do is control it. You introduce a perturbation, so you introduce a localized specific perturbation, and you watch it grow, and it evolves downstream space, time, it's evolving downstream, and that perturbation is spreading. It's called a slug in this field, okay? And as I said, it's known classically. This is a plot from Don Coles. This is a fantastic paper from the Marseille meeting, 1961. So we're going to plot speed as a function of Reynolds number. The downstream front is moving faster than the upstream front, so they spread apart, and that's the growth that you see. Let me just say that it's important that this is the mean speed, and so this upstream front is propagating against the headwind. And that is really important because, just to be clear, you have entrainment of turbulence. Laminar flow is being entrained into turbulence here, okay? It's just an artifact that it's going downstream. There's a conversion of laminar flow to turbulence there, and it's really key to what is going on. We can understand all this. I won't explain the full thing, but the fact that these come together but below, below the mean speed is significant, and blah blah blah. Okay, all right. So everybody understood this long ago. I'm going to read some of this paragraph to you in a few minutes. This is from Landau and Lifshitz. Coles understood it. Yves Pomeau understood it very well, all right? And you can see, let's not make a complicated story. No, let's not make a simple story complicated. Basically, you view it as there's a free energy with two minima, one corresponding to laminar flow, one corresponding to turbulent flow. And if I just told you that, you could work out what is going to happen. So the idea is you have two states, one of which is stable, one of which is metastable, one of which is stable, and the stable state will invade the metastable state. Hopefully that's clear. Let me go on. So the idea is, this is essentially what Yves Pomeau wrote down as a way to think about it. Q is the turbulence intensity, and it's evolving according to this equation. But the main thing is, and this should be labeled, there's a potential or free energy as a function of this turbulence intensity. 0 corresponds to laminar flow. There's always a local minimum there because laminar flow is always stable in these problems, at least over the range of Reynolds numbers we care about. Then the turbulence may be at a higher potential or it may be at a lower potential, and that determines what's going to happen. All right, so this idea is simple. If you're in this situation at moderate Reynolds number, turbulence will collapse. If you're in this situation, the turbulence will grow. All right, and again, let me just read you. This is from my copy of Landau and Lifshitz, and I'm going to kind of paraphrase. If R is above the critical value, undamped steady motion is not possible. Turbulence will, if any occurs in any section, will simply contract, as shown here. If you're above the critical Reynolds number, over time it will grow and fill up the entire domain. And then he gives conditions and this, that, and the other thing. So basically, he's describing this situation. He's describing it as a first-order phase transition, and he understood all this. Okay, so it was, and again, it's pretty simple. You could have worked it out yourself, I'm sure. Okay, and so this is generically what fronts will do in this system, and that's what the experimental measurements look like. Oh, by the way, this is where the turbulence ends as a metastable state, and there's only laminar flow below there. Okay. So what's the problem? The problem is it misses what everybody cares about right now, which is this transitional regime here shown in this plot of Coles. Coles knew the transitional regime, question mark, what happens here? He knew that there were states below this crossing. He knew that they were there. And so he wondered what's going on. And it's this intermittent regime. Okay, so that's what we care about. So when they come together, they don't just die. There's intermittency there. Okay, so I'm now going to explain the mechanics of puffs and slugs. And this, again, I just can't get over this paper. Don Coles understood all this perfectly well. He never wrote down any equations, but he understood what I'm now going to tell you. So this is the way. It's easier if I start with a slug. A slug is one of these expanding bits. I don't care about the fact that it's expanding. So let's look at it. So what we have up here upstream, this is laminar flow, fully developed laminar profile. And you should think of that as fuel, as Mike Graham has pointed out. This is fuel for this, and this is a flame front, okay? There's a lot of kinetic energy in this parabolic flow profile, which is flowing into that. I told you that these are moving relative to each other. Relative to the mean speed, this is moving to the left. This is moving into that. And it's taking that kinetic energy in that parabolic profile and burning it and converting it into turbulent fluctuations. Production exceeds dissipation. There's a rapid conversion into turbulence there. That then, where you've extracted energy from that, so that blunts that shear profile, all right? And then it flows downstream, and then you come into an equilibrium between production and dissipation. And this is just what we call, if you open up Steve Pope's book, this is just what's called turbulent pipe flow, and it's this balance, exact balance between this production term and the dissipation, and that's it. And that's the full story in some sense. All you have to work out is what the shape of that profile is to balance these things off, and then you're done. Okay, so that's that we understand very well. Now let's imagine that I'm going to decrease the Reynolds number. That's when I increase the dissipation, increase the viscosity. That term doesn't change. This one does. Eventually, I lose that balance. These are subcritical flows, so that happens discontinuously. That balance is lost, and that the core of this slug collapses. All of this downstream part can no longer sustain as an equilibrium. This equilibrium cannot hold. It collapses. It's gone. However, as I told you, we started with a situation in which production was greater than dissipation at this upstream front. You can see it's more intense there, and that survives this transition. So you decrease the Reynolds number, and that will collapse, yet this can remain intact. And that is what happens, and that's what a puff is. Okay, so you have this fuel coming in, it gets burned, it blunts the profile. The turbulence can no longer be sustained in the presence of that blunted profile, so the turbulence decays. It's a reverse transition, which I learned from Srinivasan how to understand that. And then you recover the parabolic flow downstream. And just to say, it's all right. Well, you see all that. This refractory tail is really quite important to the full story. The fact that there's a certain region down here before this has recovered enough to generate enough fuel to burn again. All right. So so we can do, I mean, we don't just draw pictures, we can do some calculations. Bofang Song did these. So this is the kinetic energy budget for slug. This is the strong production at the upstream front. This is the core of the slug where you get this balance. This is actual computed data, even though it doesn't look that way. This is the downstream front. 5 minutes, okay. Let me go on, let me speed up. Oh yeah, 5 minutes, no questions though. All right, just to show you, these are, I want to make one point here. There are actually two kinds of slugs. Nigel mentioned this very briefly. There are ones that you have a strong downstream front where you're in training flow downstream, and then you have another kind. What I really want you to see from this is notice that the upstream front is continuous as you decrease Reynolds number, going from the slug regime to these localized puffs. That front just stays the same, and you can see what a puff is. It's just what survives from there. That's the message I want to get across. Okay, and you'll see this in this movie here. Now, I can see this very well. Let's just watch it. So we started with a turbulent flow, and Bofang decreased the Reynolds number. You get to a regime where you have the puff, and the turbulence doesn't all collapse. It starts to, it wants to, but then eventually you generate puffs, and they'll be kind of randomly spaced. So this one can exist, or let's take this one. This one could exist. This one burns some fuel, and then there has to be a recovery of the parabolic profile, and then you can burn in some more, and then it has to recover and burn some more. I could spend a long time talking about that. I'm happy to answer questions, but I think the general idea is there. That's what happens when you lose this steady state. You don't lose turbulence everywhere. You can still sustain it in these localized patches that we call puffs. So what do we have to do? We had this model, which I claimed is perfectly adequate at high Reynolds number, but we have to now take into account that there's this, particularly in transition, there's this the shear profile plays a role, that when you have laminar flow, it's like this. When you have turbulent flow, it's like that. You have to put in the negative feedback of this shear profile. And there's a bunch of papers on that. So here's a model. So now I have two variables, turbulent intensity and state of the shear profile. Or you can think of it as center line velocity is a good proxy for that. We're going to say here. And to orient you, this is fully developed laminar flow. The turbulent intensity is 0. And the laminar profile is as large as it's going to get. I have two kinds of dynamics. I have the dynamics of the shear profile. So when turbulence is, let me just put it on here. When turbulence is large, the shear profile blunts. When turbulence is non-existent, you recover to the laminar state. This is the turbulence, is just the dynamics I gave you before, two stable fixed points with an unstable one in between, now depending on the state of the mean shear. Okay, and you put those together, and you get phase diagram that looks like this. Anytime the red and the blue intersect, you have a fixed point. That corresponds to fully developed laminar flow. It exists and is stable for all values of the Reynolds number. As I increase the Reynolds number, I get another fixed point where I get an equilibrium between the turbulence and the shear profile. And when you do this, then you have two kinds of states. And let me just put everything on here at once. Let's just do the slug. So this is a slug. I start here with laminar flow. I convert. The turbulent intensity goes up, the shear profile blunts, I reach an equilibrium, and I'm happy, and I exist, okay? That's all there is. For the puff, you can see what's going to happen. I'll just put all these arrows on. Upstream, I'm in laminar flow. I generate turbulence, the shear profile blunts. I don't have an equilibrium to go to. The intensity decreases, and then the laminar profile recovers. Okay, let's see. So we have an excitable and bistable situation. Okay, and that's actual DNS of pipe flow. That's the turbulent intensity. That's the centerline velocity. What does this look like? Anybody in the audience who works in neuroscience? An action potential. It looks just like an action. I'll come back to that. Summary. So fundamentally, the route to turbulence in many wall-bounded shear flows is driven by a transition between excitability and bistability. That's the key thing, in my opinion, where the excited state is fluctuating, highly fluctuating. And then interplay between these two, together with downstream advection, will account for essentially all the phenomena that we see, all the large-scale phenomena. And we think similar thing. I only talked about pipe flow, but we think this applies elsewhere. This is just I'm going to wrap up here. This is the front speed versus Reynolds number. This is the points on here are modern data from Bjorn Hoff's group, experiment and simulation, and the lines, which you can barely distinguish, are what the theory gives you. It wasn't designed to be this quantitatively accurate, but it just tells you something. There's a lot of details in there that I could talk about. It gives you puffs and slugs. It gives you the intermittent regime. It gives you the critical point with the directed percolation transition. It gives you all these phenomena. You can extend it to other models. Now, I'm just going to say something real quick. I just want to make a real point, very minor. Nigel and I are in a lot of discussions about this. I just want to say that it's not really settled science that the zonal flow plays a role here. I don't agree with that. I mean, I think that the streamwise shear is much more important. There are fluctuations. There's a lot of fluctuations, and it's just not clear to me that zonal flow is the relevant one. And with I'm going to jump ahead just real fast, and I'm going to end with something positive and just show you this is actual pipe data. That's a cartoon. This is actual neuron action potential. That's a cartoon. But you see, you get the point. Okay, thank you.
What would it take to make a neuron do all that your pipe flow does?
Oh, how do I tried to go back and I went forward again. Sorry.
Sorry, here.
No. I was going to have to. I was going to show. I think. Okay. Here's what I think to be true, and have a lot of evidence that if you just again, you're taking a neuron, but then you have to have a bistable transition. You have to stabilize that upper fixed point, that upper state. The excited state has to stabilize. You add fluctuations to that, and I've added a lot of different fluctuations, and then you get. Let me see if I can go backwards. All of these phenomena, I will speculate. Let's put it that way. Come out generically. These are model, and this is reality, and this is model. This is reality, and this is model. I think it's just transition from excitability to bistability with fluctuations. Generically, give not in every. No, I'm not sure. Give almost everything, if not everything. That's my view. Yeah, Nigel might want to say. Your button.
A neural network model of that, like a Wilson-Carroll model, and you write it down as a StatMech model, you'll find that this is an universality class of a directed percolation, just like Dwight is saying.
Yeah.
That's what I was curious about actually making it happen on a giant taxon.
Oh, yeah, well, okay, that's... I'm good? Oh, no.
How much of this can be extended beyond the geometry of a pipe flow? And is that
so that's here, let me just show you something here again. Am I going the right way? I'm going back. Sorry. Unfortunately, this is not going to be ideal. It's going to... There. Oh, God. All right. Okay. The problem with extending it to planar flows is we know a lot about what the mean flow, the equivalent of my mean shear, and it's more complex. Pipe flow, just a lot of things came together such that the complications of the mean flow is very simple. All right. So we get some things about planar flows correct, but there are fully two or three-dimensional effects that I don't know how to account for. What I always tell people, and the reason I haven't done this for the past 10 years, been thinking about it, is I think you have to, in some sort of modeling, whatever context, you have to think about an elliptical problem. You have to solve some sort of global problem to get the mean flow, to get the right behavior of that kind of simulation. That was real hydrodynamics I showed you with the black and white, the movie at the beginning. If you look at those carefully, you'll see that they're kind of propagating and doing complicated things. And none of this, I mean, they give the right kind of percolation behavior, but the global behavior in the two-dimensional plane is never right. Nobody has cracked that problem. And obviously, if I knew how to do it, I would have done it 10 years ago. Well, it's easier to say I don't know. How's that? I mean, we can discuss it. How it may be. Yeah.
Yeah, a quick question. How much, and you say there's a fixed point jump for synchronization between different points, divides in notation.
Ah.
Yeah.
Well, that's a good question. I don't know.
Right now, no notation, right?
That's right. That's right. Actually, people have done experimental work on that, but I haven't thought about it, so let me not answer. Yeah, we work in a regime in which that's not. I mean, we work in a counter-rotating regime in which you're with a very, very small gap, and it's not a very important parameter in that regime. Again, it's actually a very good question, and I'm surprised somebody hasn't asked me before, but I'd like to think about it and talk to you later.
First of all, I'd like to turn my mic on. Second of all, I'd like to thank the organizers for the opportunity to speak here. I'm kind of carrying the flag for complex fluids. I was happy to see that there's a poster on complex fluids as well. So I'm going to talk about various aspects of turbulent flows in complex fluids, and in particular, let's see if I can get everything working here. My technology. There we go. All right. So first of all, rather than end with my acknowledgments, I always forget them at the end, so I'm going to put them at the beginning. So most of the work that I'll talk about today was done by Ashwin Shekhar, and some with Ryan McMullen and Beverly McKeon, who are collaborators at Caltech. And the problem that we're interested in is an observation that's been known for quite some time, since World War II, that if you add small amounts of long-chain polymer molecules to a fluid, then you can dramatically reduce the energy consumption in the turbulent flow regime. All right, so the canonical application for this phenomenon is the Alaska pipeline, where they add small amounts of oil-soluble polymers at every pumping station, and it dramatically reduces the energy consumption. So this is a widely used phenomenon. It's used in various types of closed-loop heating and cooling systems, or actually, in this case, they often use surfactants that form worm-like micelles, which behave like long-chain polymers in some sense, and then fracking fluid formulations do something similar. As a really nice example of this, so this is, it used to be the case that Union Carbide, which no longer exists, was selling rigs that would add polyethylene oxide, a very long chain, very inexpensive polymer, to water for firefighting applications. So this is an old picture. You got some firefighters over here, and here's the spray of water, and here's the spray of rapid water from Union Carbide. And you can see, presumably this is the same pressure drop. I hope they did the control right. Presumably, so, and then you can see that the stream of rapid water goes much further than the stream of regular water. So that's a very clear visual indication of this drag reduction phenomenon. So why isn't this used in firefighting today? So I actually contacted a company that sells firefighting equipment, and their president sent me to a website, nycfire.net, and they have these blogs on this website. And so this is from the 60s. In the FDNY, rapid water was used for a few years. And the problem with it was that if you spilled some of this stuff on the floor of your firehouse, then everybody slid around. And so it was actually a hazard to use in firefighting applications. But anyway, this is a very nice example of the phenomenon, and it's something that's widely used today. And so what my group has been trying to do for many years now is gain some fundamental understanding about the interaction between the polymer dynamics and the turbulence. Okay, let's see if I can. Oops. All right, and so since this is not necessarily a rheology crowd, I thought I would provide a one-slide tutorial on the dynamics of dilute polymer solutions. That's the primary situation of interest here. So a long-chain polymer molecule at equilibrium, roughly speaking, is a random walk along the chain backbone. It's got some contour length. Right, each random walk step, and then it's got an equilibrium length, which is, if it's a regular random walk, is the square root of the number of segments. So that gives you a measure of the size of the chain. All right, and then you can think about a relaxation time for that polymer molecule. If you stretch it out It's going to take some time to relax. And that time scale, roughly speaking, goes as the amount of time it takes for that polymer molecule to diffuse its own size. All right, so there's a relaxation time for the molecule. All right, so we're going to call that lambda. All right, and so there's a non-dimensional group that comes out in every flow problem involving polymer solutions, and that's the Weisenberg number, which is the product of a relaxation time and some characteristic strain rate in the flow. Okay. The related quantity, the elasticity number, is the Weisenberg number divided by the Reynolds number. And then the other key thing to understand is that the response to kinematics. All right. So we're going to model, we and just about everybody else, we're going to coarse grain this into a very simple model. The simplest model is just a dumbbell that's characterized by an end-to-end vector Q. And that dumbbell can stretch and orient with the flow. And to a first approximation, that dumbbell wants to stretch and orient like a material line. All right? So material line dynamics are important in understanding what's going on as a polymer molecule interacts with a flow. So if a shear flow, material lines stretch linearly in time, and the combination of the relaxation and Brownian, well, actually, the relaxation, the reorientation, they're all due to Brownian motion fundamentally. So you don't get strong polymer stretching in simple shear flow. Okay, and so the situation of interest for drag reduction is the case where the polymer concentration is low enough that you don't change the shear viscosity very much. And in our case, the shear viscosity, this parameter beta, 1 minus beta will be proportional to the concentration. And so 1 minus beta will be close to 0 for a dilute solution. All right. So this is just the viscosity of the solvent divided by the total viscosity. Extensional flow is another situation. In an extensional flow, material lines stretch exponentially fast. And if the polymer molecule is long enough, if its relaxation time is large enough, then the molecule will stretch exponentially fast as well until it reaches its full extension. All right, and so there's a characterization of the extensional viscosity of the polymer molecule. And even when 1 minus beta is small, this extensional viscosity is 1 minus beta times some function of the ratio between the fully extended length and the equilibrium length. And so this quantity can be very large even when you have a very dilute solution. Okay? And so that's key to the drag reduction phenomenon. All right? And then we've heard a lot about vorticity in turbulence, but everything in between the vortices is extensional in a turbulent flow. So if you have a chaotic velocity field, in general, material lines stretch exponentially fast, and you get exponential stretching of polymer molecules. And that turns out to play a role in my story later. All right, so there's my tutorial. So here are some of the key observations from the drag reduction literature. So one of them is that if you just plot the classical friction factor versus Reynolds number, this would be Newtonian laminar, this would be turbulent. A wide variety of data actually falls on this same curve, which is called the maximum drag reduction asymptote. And that's something that people have been very interested in this field for some time. One thing I want to point out here is that this behavior extends down into the transition regime. And that's where we're going to be working today. All right. And then, so this is a talk, this is a meeting on universality in turbulence. So the universal features are this curve of friction factor versus Reynolds number. And then roughly speaking, the mean velocity profile, so if you back out a law of the wall, a logarithmic velocity profile from that, you get this curve here, which Verk did. If you actually plot data, this is data from simulations and experiments. The data doesn't quite lie on that. It kind of is smeared around that. But roughly speaking, you have this a nearly universal behavior in the mean velocity profile. Okay? So that's the maximum drag reduction phenomenon. And I'm not going to say we will have completely explained this by the end of the talk, but hopefully we'll make some progress. Okay? Structurally, the dynamics of the flow are significantly changed when you have drag reduction. And classically, this was viewed as being modifications somehow, and I'll explain this in more detail how, modifications of the streamwise vortices that characterize near-wall turbulence, all right? And so these are just some snapshots of experimental data showing this. So this is channel flow. That's the flow direction, and you see in all these cases, you see this streaky behavior, which is modified by the polymers, and the same in here. All right. So that's sort of the classical picture. These papers are 10 and 15 years ago. All right. Recently, so there have been some very interesting observations that suggest that there's a somewhat different picture at high values of elasticity, high Weisenberg number, and in particular. So there's some experiments from Björn Hoff's group and computations from Yves Duvieff's group, where they found, this is a picture from Yves, where they found very weak vortex structures that were not aligned in the streamwise direction, but aligned in the spanwise direction. So that's a very different structure than you find in Newtonian turbulence. And so this regime, at high levels of viscoelasticity, relatively low Reynolds numbers, this was called the elasto-inertial turbulence. All right, so that's going to be one of the topics of my talk today. And so we'd like to gain some understanding, some fundamental understanding of this phenomenon. All right, and then last bit of background. This is a very interesting observation. This is again from Björn Hoff's group. So this is a pipe flow experiment, and what they did was quasi-statically increase the concentration. So they're in polymer concentration. So they're increasing the contribution of the polymer molecules to the stress in the flow. And let's focus on this plot here, which is at relatively low Reynolds numbers. So zero concentration, this is Newtonian turbulence. Here, as they increase the concentration, the friction factor goes down, the drag goes down. And then above some concentration, they actually find that the flow laminarizes. And then at higher concentration, the flow becomes turbulent again, very weakly turbulent, all right? And so this is, they identified this as elasto-inertial turbulence. So the punchline of this observation is that it points very clearly to the existence of two types of turbulence in the solution. One that's suppressed by the polymer and one that's promoted, all right? And we're going to try to make some progress in understanding those observations. So what we'll do, I'm going to talk about direct simulations in the channel flow geometry at low Reynolds numbers, so transitional Reynolds numbers, where we don't have a vast range of scales. We're not doing, where's Dwight? So we're not going to do a box that's 1,000 by 1,000. Okay, so we're gonna focus on just the near wall structures. All right. And the first part will be how viscoelasticity modifies the near wall dynamics. All right, and the second part will be how the viscoelasticity promotes this elasto-inertial turbulence. Okay, so that's the story. Just a very few words about the model and the simulation. So there's our dumbbell model. There's a particular type of model, FINI-P, finitely extensible nonlinear elastic dumbbell model. P is for a particular closure approximation. You can write down a closed form expression for the evolution of the stress in that case. And I'll just mention briefly, I know very little about magnetohydrodynamics, except that in magnetohydrodynamics, the field lines are stretched as material lines, and the stress tensor is proportional to the dyad BB. Here, the polymer molecules are stretched as material lines, and the stress tensor is proportional to QQ. All right. And so we've got Navier-Stokes This is the evolution equation for the Feeney-P model, and we're solving this with methods that don't have artificial, actually the more recent results are methods which don't have artificial stress diffusivity. All right, and I can answer other questions about that. All right, so the first topic was what happens at low to moderate Weisenberg number. And so we addressed this question by looking at the dynamics in so-called minimal flow units. So these are domains that are basically as big as one pair of streamwise vortices. And so this is a method that's been approach that's been used for a couple decades to try to understand near wall turbulent structure. And so we're doing this in the viscoelastic case. And a couple key observations. So let's start with this one. So this is at a Weisenberg number of 29. And this, let's just look at this bottom case here. This is just wall shear stress at basically a line at constant streamwise position as a function of time. There are lots of fluctuations here. These regions here, those would be low speed streaks, so those are low wall shear stress regions. And what comes through here is there are long intervals where the dynamics are relatively smooth. And if you look at this plot here, for example, this is the mean wall shear rate. And you see these very large fluctuations in the mean wall shear rate. All right. Here, this is just some estimate of the slope in the logarithmic profile. These are very low Reynolds numbers, so don't take this too seriously. It's just a measure of what the velocity profile looks like. And what's interesting here is that that's popping back and forth between a low number that would be characteristic of the Newtonian log law and a much higher number that would be similar to the Verk MDR log law. So they have this sort of two-state behavior, this hopping back and forth. Interestingly, even in the Newtonian case, every once in a while, you'll see one of those low drag, very quiescent intervals. And actually, Fabian Willef is here. He's the W in that paper there. And so this had been observed in other simulations in minimal channels. Okay, so these low Reynolds numbers, you have this intermittency that becomes much more pronounced in the presence of polymer. All right. So we can characterize that. We can characterize the average duration of these intervals. All right, and just for the sake of having some nomenclature, we called the regions where the turbulence looked relatively normal, we called those active regions. So if you looked at the instantaneous mean velocity profile, looked like a Newtonian profile. The hibernating regions had a profile where the log law was well above the Newtonian case. So we have active and hibernating; those are kind of the two states. And so what's interesting here is if you look at the duration of these active intervals and the duration of these hibernating intervals as a function of Weisenberg number, very little happens to these hibernating intervals up to Weisenberg number, say 30, all right? Whereas the active intervals, very little happens to them until Weisenberg number is 10 or so. And the reason the fluctuations are big here is that the errors are big there is because these happen so infrequently in the Newtonian case that we weren't able to gather great statistics for it. They just don't happen very often. All right, but once you exceed a Weisenberg number of 15 or so, now the duration of these intervals goes down, and actually you see there's this nice curve. And so the picture of the near wall dynamics in this case is that you have these active intervals, which correspond to strong, highly three-dimensional streamwise vortices, and those get suppressed by the polymer dynamics, whereas these hibernating intervals, which are much weaker flow structures, they're not laminar. I'll show you the structures in a moment. All right, they have much weaker flow structures that are not nearly as strongly affected by viscoelasticity. So this is a movie. It's an old movie by now. This is probably the thing to look at here. So the green, that's just a surface of constant streamwise velocity. And the little crease there, all right, that's an upwelling. That's a low-speed streak. And so you have very weak streamwise vortices. So this is during one of those hibernation intervals. Very weak and very nearly streamwise invariant structures. If they were fully streamwise invariant, there's no mechanism for turbulence to sustain itself, and you'd laminarize. All right. But that hibernation interval ends, so the red, those are vortex cores, and now you start to see the typical near wall vortex, three-dimensional vortex dynamics. The instantaneous mean velocity profile goes back down. So you have this alternation between these very, very weak vortex states and much stronger vortex states, all right, that are characteristic of the Newtonian flow. So you can make a picture of that, just roughly speaking. So in the active turbulence, so we have relatively strong streamwise vortices, and those are actually quite good at stretching the polymer molecules. All right, and so then those active intervals end as the polymer stretching suppresses those streamwise vortices. And actually, we understand the mechanism pretty well of how that works. So this picture here, this is looking at polymer stretching. And what you see here, in this upwelling, you have highly stretched polymer that comes up and begins to wrap around the streamwise vortices. In the vortex cores, the flow is no longer extensional, and the polymers start to relax. And if you just look at the associated torque from the polymers, they basically work to unwind the streamwise vortices. So we understand that mechanism reasonably well from work of our group and a number of other groups. And so these will collapse, and you end up with this much weaker state. In this case, the polymers relax. They're being very weakly perturbed by the flow. The main effect of the flow here is the mean shear. The vortices have a very weak effect. Eventually, these states go back to the active case, and you sort of cycle stochastically through here. And the plot in the middle is just a joint PDF of the degree of polymer stretching versus the local velocity, the strength of the local velocity profile. All right, and what's interesting here is when the stretching is high, basically the velocity profile looks more Newtonian. When the stretching is low, sorry, did I say that right? When the stretching is low, you're out here where you have the higher, basically higher velocity. So there's this interesting anti-correlation between the polymer stretch and the drag. And it's because in this region, you're stretching the polymers, and in here, you're relaxing them. All right, so that's sort of a physical picture of what's going on. We can make a little theory about that. And the basic idea of that little theory comes back to, what I described earlier, which is that the polymers will tend to stretch like material lines, but then relax with their characteristic relaxation time. So we can make a little model that says in the active intervals, the polymer molecules are being stretched and relaxing. And so the stress, or polymer stretch, will be an exponential function of, sigma would just be the largest Lyapunov exponent for the velocity field, so the material line stretching rate. The factor of 2 is because stress goes as line length squared, q squared. And then, but the polymers are relaxing against the flow, and so what matters is the relative magnitude of those two quantities, all right? And so then what we do is we just make a simple hypothesis that once the Weisenberg number exceeds some value, then the duration of one of these active turbulence intervals is simply the time it takes, the time that the polymer stress remains below a certain threshold value, okay? Very, very simple model. Once the stress exceeds a threshold, then the polymers kick in, they suppress these vortices, all right? And so if you do that, and it turns out you can replot the result as a linear, so the inverse of the duration is a linear function of 1 over the Weisenberg number. And so here's just a plot of those two quantities. And so above some critical Weisenberg number here, you get a straight line for that. All right. So that says that the duration of these active turbulence intervals is just controlled by how long it takes to stretch the molecules out to some threshold value. Okay, so that's a simple toy physical model for what's going on here. All right. We can connect this with a more, at least in a hand wavy way. We can connect this with some of the dynamical systems ideas that have been developed for understanding near wall turbulence. And so again, this comes back to Wally's work. So we know that in these flow geometries, there are nonlinear traveling wave solutions to the Navier-Stokes equations that look like near wall vortices. They're saddle points in state space, but the turbulence essentially looks like these structures. So these are, so the red here, those are vortex cores, and this is a particular solution. This is another solution. It's the same solution family, upper and lower branch solutions. This one is quite vigorous. This one is very weak. And so if you make a state space projection of wall shear stress, dissipation, kinetic energy, you can plot these solutions on here. You can look at the dynamics. And so in the Newtonian case, you have these infrequent excursions down toward these lower branch states. So that's the infrequent hibernation intervals. What happens in the viscoelastic case is that the vigorous turbulence here, it gets suppressed and the dynamics get driven down toward these lower branch solutions as the upper branch solutions are suppressed. Okay, here for this solution family, we've only done the calculation for the Newtonian, so these are all the Newtonian. Okay, so that's sort of a qualitative picture of what we think is going on in this situation. All right. Now, as the Weisenberg number increases further, these coherent states collapse. All right. So that is kind of the end of the first part of the story here. Okay. So we have these sort of two different types of near wall turbulence. They're both present in the Newtonian case. One is only sampled very infrequently by the dynamics. As the Weisenberg number increases, the active turbulence intervals are suppressed because the polymers are strongly stretched in those time intervals and suppress those vortices. All right. So in a sense, that's the first part of the story. So that's how the normal Newtonian turbulence gets suppressed. So the rest of the story is trying to understand this elasto-inertial turbulence phenomenon. All right. So that's what I'll spend the last few minutes on. All right. Okay. So then now what we've done here is move to lower Reynolds number, close to transition. And we're in the channel flow case rather than the pipe flow case. So in channel flow, Newtonian transition is a Reynolds number of 1,000. All right, so we're going to work at Reynolds number of 1,500, so just above that. All right, and so these are some simulations that got published earlier this year. So this is the analog to the experiments that Björn Hoff's group did. Here, instead of increasing concentration, we're keeping the concentration low and increasing the Weisenberg number. This is just normalized friction factor versus Weisenberg number. Here's the Newtonian, there's the Newtonian point, okay? So as you increase Weisenberg number, friction factor goes down, but eventually, in this case, you laminarize. As you increase the Weisenberg number further, sufficiently energetic perturbations will go turbulent again, and that's this regime here. So this is very closely analogous to Björn's experiments. These are the flow structures in those two regimes. So here, right, these are vortex core structures. So you can see the streamwise vortices that you expect from Newtonian near wall turbulence. So I just told the story about how those are affected by the polymer dynamics. All right. This picture over here, this is very similar to what I showed you from Yves Dubieff's work a couple years ago. All right. So qualitatively have very different dynamics in these two regimes. All right. So the rest of the talk is going to be to try to gain some understanding of what's going on in this regime. All right. So one thing that we can do is just take a slice through here, and let's just look at the fluctuations. And one thing I'll point out here is that these are 3D simulations, obviously, but the structures are sort of two-dimensional. And actually, you can show that two-dimensional simulations in this regime will still lead to turbulent dynamics, chaotic dynamics. All right? So we can take a slice of the velocity and stress fields here, and this is just a snapshot of that. And what's really striking about this is the following. The color contours are the polymer stretch fluctuations, all right? And the XX component is the largest component. That's the polymer stretching in the streamwise direction. And what you can see here is that those fluctuations are very strongly localized, all right? Some offset from the wall. And the contour lines are wall normal velocity, and you can see that there's some localized fluctuations and some larger fluctuations as well, all right? But what's really striking is these localized stress fluctuations. And this localization is reminiscent of observations from very classical hydrodynamic stability of critical layers. So a critical layer is a position where the mean velocity is the same as the wave speed of some kind of wave structure. All right, and so if you go to Drazen and Reed, go to any classical book on hydrodynamic stability, there are big sections on the dynamics associated with critical layer behavior. And for example, in inviscid shear flows, there's a jump in the Reynolds stress at the critical layer. All right, so we see something similar here, and in particular, we can think about the classical linear stability mode for wall-bounded shear flows, and that's the Tollman-Schlichting wave. All right, so let's look at what Tollman-Schlichting waves look like here. So there's a Tollman-Schlichting wave. So just solve the linear stability problem for this viscoelastic flow, and I should point out this was done by our collaborators at Caltech. And again, you see this very clear localized structure. All right. Now, Tollman-Schlichting waves in Newtonian turbulence, they don't play a big role. They don't show up. They don't bifurcate until Reynolds number of 5772. Channel flow is turbulent by Reynolds number of 1,000. TS waves are two-dimensional. Newtonian turbulence is three-dimensional, dominated by streamwise vortices. All right. But this is looking very much like what we are seeing in this elasto-inertial regime. Okay. So we've looked at some of the linear problems here. So this is the linear stability problem. I should point out this is decaying. Everything I'll talk about here is in the linearly stable regime. The laminar flow is linearly stable here. All right. But you have this traveling wave mode that's decaying. You could look at the problem from a slightly different point of view, and again, this is from our collaborators, where you look at the response of the linearized Navier-Stokes plus Fini-P operator to external inputs. So that's the resolvent analysis. One way to think about it is it's just writing down the transfer function for the linearized Navier-Stokes equations. So you can look at that as well, do singular value decomposition of that operator to find the largest singular value, so the structure that's amplified the most. That's here. That's almost identical to the Tollman-Schlichting mode, which isn't necessarily surprising. All right, but both from the resolvent and linear stability analysis, we see this structure arising. So we can make a comparison between the DNS, the snapshot from the DNS. Here, we've just filtered out the 2-0 Fourier mode, so two waves in the horizontal direction, which you can see from the picture. We've just filtered that and then phased aligned different snapshots and then averaged over them. And then what you see is a structure that looks very much like the TS mode or the leading resolvent mode. And in particular, you see the same symmetry. In fact, where there's high stress fluctuations here, there's low on the other side. That's the same symmetry that's obeyed by the Tolman-Schlichting wave. Okay? So in the last 28 seconds, I'm going to cut into questions a little bit here. We've done 2D simulations now, trying to look at how the Tolman-Schlichting wave evolves with viscoelasticity. So on the vertical branch here, that's the Newtonian case. This is just mean wall shear rate. So in 2D, the Tolman-Schlichting, the nonlinear Tolman-Schlichting wave bifurcates subcritically, and so it exists at finite amplitude down to a Reynolds number of about 2800. And so we can find that solution branch. Okay, and that loses existence above a Weisenberg number about 3, and you go to laminar. Here's 2D EIT simulations. All right. That loses existence around Weisenberg number 13, but below this turning point here, you actually don't laminarize. All right. You go to a very weak nonlinear state, all right, which turns out to look like this. So that's the linear Tolman-Schlichting mode. This is the self-sustained nonlinear state in the viscoelastic case. And you can get to this just by tweaking the laminar state with the linear Tolman-Schlichting mode. So there's a nonlinear self-sustained nearly traveling wave state here. It's a little bit non-periodic here, but it's clearly organized around the Tolman-Schlichting wave structure. If you use the laminar plus a big perturbation of the Tolman-Schlichting wave, you'll get to elasto-inertial turbulence. If you have the laminar plus a tiny, tiny, tiny perturbation, it'll go back to laminar. You still have linear stability. But one thing that's quite striking here is that if you look at the maximum amplitude of the polymer stretch versus the velocity, it becomes quite enormous at high Weisenberg number. So this linear mechanism is generating enormous polymer stretching for a very tiny velocity field. And that's, we find quantitatively similar results for this self-sustained, we call it a viscoelastic nonlinear Tolman-Schlichting attractor. We call it the attractor rather than wave because it's not always a pure traveling wave. All right. Okay. And so, oh, I left out a slide. Damn it. That's okay. So the slide that I left out is just looking at this ratio as a function of Weisenberg number. And what's interesting is that once the Weisenberg number is around 4, that ratio really ramps up, and that's where and Weisenberg number of 6 is where this nonlinear traveling wave solution comes into existence. All right. So just coming back to here. All right, the point is there are 2 branches of nonlinear Tolman-Schlichting waves. There's a Newtonian branch and an elastic branch that kind of goes like this. All right, and the organizer, the chair is standing, and so I will go to my conclusions. There we go. So we're gaining some mechanistic understanding of the interaction between polymer dynamics in turbulence. We have a good understanding of what happens to the quasi-streamwise vortices that are the foundations of Newtonian near-wall turbulence, and we now are starting to see that, that viscoelasticity is exciting the Tolman-Schlichting wave structure that's linearly stable, but strongly excited by viscoelasticity. And we can think about maximum drag reduction in terms of these 2 effects competing with one another. And this is just a snapshot from a simulation, a little higher Weisenberg number, where we see both. There are plume-like dynamics, which are characteristic streamwise vortices. There are these thin sheets that are characteristic of the elasto-inertial turbulence. And MDR may be some competition between those. The vortices are suppressed by viscoelasticity, but the TS waves and other structures, there's other stories besides my own on linear modes that show up at very high Weisenberg number. Those may be important as well. And so with that, I will wrap up. I'd be happy to answer any questions. So we not in the time domain. So in a sense, the resolvent analysis is doing that in the frequency domain. So in the time domain, there are other people who've looked at that, and there is strong amplification. All right. But yeah, so that's not our story, and that's not as directly connected as the frequency domain work is. Yeah.
Just another quick one. What's the initial amplitude with respect to the centerline flow for this nonlinear Chaumian shift?
Oh, they're very, if in the velocity, they're very, very small. It's really quite striking how small a perturbation is necessary to move you away from laminar. So the laminar is linearly stable, but the linear regime is very, very tiny. Yep.
Okay, let's thank Michael again.
So I decided to change my topic a little bit, partly because Sasha talked about circulation this morning, and I didn't know whether you would have the patience to listen to my talk as well, but I'll say something about it. But I would also want to make some connection with a few other talks at this meeting. So I'll give you 3 examples of the sorts of things we've been doing in recent years using massive 3D simulations of Navier-Stokes equations. I don't know whether there will be a simpler model than Navier-Stokes, but we'll see. For the last few years, along with these people, we've been working on the first problem here, which is the theory on the origin of turbulence. And I really don't know whether it's obvious that a general theory would actually work for this, but things are accumulating in its favor. And we published some of these in these papers. And I want to give you a little summary of the concept, basically, not go much further. So take homogeneous and isotropic turbulence in a periodic box. And initially, you start with low wave numbers of a rapidly oscillating, or as people call it, delta in time, random Gaussian field. So evolve it using Navier-Stokes equations on a discrete grid with sub-Kolmogorov scale resolution. I mean, it's resolved really well. And evolve to a state of statistical stationarity. And then compute various quantities, for example, energy dissipation and its moments, say Mn for n 2 to 6. That's the exercise. And what you find, I've shown you schematically here, if you take a moment of order n1, there is, as a function of Reynolds number, there's a range of Reynolds number over which it assumes a value that is equal to that of the Gaussian, 2n minus 1 double factorial. And then at some Reynolds number like that, let's call it transition Reynolds number corresponding to n1, it takes off on a power law with an exponent here that is equal to that of fully developed turbulence. And if you go to a higher moment n2, that too behaves like that, but it takes off at a different Reynolds number, a lower Reynolds number than for here, because the moment order is higher. And this power law is again characteristic of fully turbulent flow. Now that's really how the data look. See, for example, for the second order, it's flat and there is a power law which is relatively shallow here. But if you take the sixth order, it actually takes off, as I said earlier, in Reynolds number than here, and goes like that. Now, of course, the transition is not as abrupt as I have indicated there, but that's the way the experiments are. Now, you can actually do a little bit of theory to rescale the Reynolds numbers in such a way that all these Reynolds numbers come on one point, and you can do a little bit more theory and say that the Reynolds number is of the order 10. So this is all published in one of these papers. But the question that I want to ask here is this scenario true more generally for, say, thermal convection, which is a very complex flow with rolls and cells, etc. We looked at channel flow at one time, and it seems to be similar. I say seems because there are still some issues to be sorted out. And this is the result for the convection flow. As a function of this Reynolds number, these moments are plotted here for n equals 2, 3, 4. You can see this in this range, they are pretty nearly double Gaussian corresponding to the Gaussian, double factorial corresponding to the Gaussian state. And in this narrow range of Reynolds number takes off again. These are not arbitrary powers, but powers that are characteristic of fully turbulent flow. It'd be nice to have more data here, and it will be generated in due course. Now, what's happening below this Reynolds number? This is very low Reynolds numbers, and that's what I will show you here. In this Reynolds number range, it is really dominated by steady state structures like these, rolls and so on, where they're very important in some sense, but the Reynolds numbers are very low because they're just sitting there and just churning around. And so somehow these perhaps are more like exponentials because these are the moment values for the exponential. Somehow the structure dominated part of the transition is covered in this range, and then it transitions itself to something like a Gaussian state before it becomes fully turbulent. That's basically the message I wanted to communicate. And here are 3 lessons that I believe we should learn. Transition to fully turbulent state has some common features, transcending the diversity of structures characteristic of each flow. The transition takes place at a low value of the Reynolds number of the order 10, and that seems to be about true for 3 flows, and therefore I resisted myself from the temptation of saying universal. And the pre-transition stage emerges to be Gaussian. I think it has some semblance to the kind of thing that was discussed earlier by Nigel. So let's talk a little bit about circulation to the next point, high Reynolds numbers. And basically, the data for this comes from box-type turbulence again. And I want to mention to you that the number of grid points in the computational domain goes from 256 cube to 16384. That's a really large computation. And pK has actually gone to 24K cube now. And the averages are performed over many realizations, so you shouldn't worry about the statistical convergence and things like that. Now, the area rule that Sasha Migdal talked about, I'll talk a little bit about circulation, as I said. The amazing thing, and I'll qualify this statement in a little bit, the amazing thing is whether you have, in planar cases, a square like this or a rectangle like this stretched out, in fact, until one of the limbs get into the dissipation range, or in the case of loops like this, figure-8 loop like this, for example, the probability density of the circulation is essentially the same. As I say, I'll qualify that in just a minute. And you can see it from here. These are different conditions and all that. And you have a stretched exponential fit for these. Whether it has any meaning or not, I cannot tell you right now. In fact, the statement that I just made has to be qualified because the area rule really becomes better and better the higher the order of the moment you consider. That is to say, it's better at the tails than, let's say, at the core of the probability density. Not only that, as Sasha remarked this morning, if you take, let's say, loops not in a plane, but imagine you have one loop in this plane, another loop in this plane, and they hit each other like that. This is what I call sucker gate. Then what is really important in this is not the actual area of the loop, but the minimal area. The minimal area, you can compute it for this, and it's about 3.24 r squared rather than 4 r squared. And preliminary calculations suggest that if you take this area, then the PDF again collapses on this. I think it's a very remarkable result. And it's not exactly clear where it falls from, but anyhow, that's what it is. And now this is one result from the calculations. Basically, if the precise geometry of the loop does not matter to a very large degree, let's take loops which are squares, and you compute the circulation around it, call it gamma of r representing a length, and evaluate its pth moment. That is to say, raise it to the power p, do it on all possible loops like this in the flow, and then you do it for many, very many r's, and you expect a power law like this, for instance, and then you do it for different p's. So it's a lot of calculations, as you can imagine, and the result is shown here as a function of p, these indices lambda p done here. What you find is, unlike the case for structure functions and so on, which depart from this Kolmogorov line substantially and nonlinearly, which is the multifractal characteristic, which is what makes the problem very difficult. That is to say, if you know one exponent, you can't rightly extrapolate to another exponent, etc. What you find is for low order moments, it's almost Kolmogorov. Actually, if you look at it very carefully, it departs slightly from there. But for high order moments, it's on one single line, sitting on another fractal set, which is, I say it's fractal because you calculate from this data, its dimension turns out to be about 2.5. So what is shown here in this insert is this difference, and you can see that for the circulation, it is like that, and 0 is the Kolmogorov value, whereas for structure functions and things like that, it is quite different from what you saw in much higher. So I think this is why we called it a circulation in high Reynolds number isotropic turbulence, a bifractal, because this is one fractal space filling, another slightly less so, that is 2.5 units. Yeah. Now, the last one is basically the major problem is to find out what the heat transport law is. That is the so-called Nusselt number, is the amount of heat transferred as a function of Rayleigh number, which is the amount of temperature difference maintained between bottom and top plates. Now, an experiment we did some years ago, where we went from 10 to the power 6 to 10 power 17, using some properties of cryogenic helium, showed that the power law was 1 and it was around 1/3. So I forget about all this. We actually looked at it very carefully and said it varies approximately as the 1/3 power. But then there is the so-called ultimate state, which is what everybody is trying to find out if it is true or not, coming from Kreighton and Spiegel, which says that the power law is like half. In fact, there was one paper, this paper, which said, well, the last 2 data points in the experiment showed a tendency to 0.38, and therefore they thought it was ultimate state, which has been challenged here and here. But in this paper, one more slide is all I have. Well, the title already suggests to you what we actually find. And again, we did this using very large-scale simulations. You see, these are the number of grid points, etc. And this is the result. So you have at Rayleigh number 10 power 11, 10 power 13, and 10 power 15. Temperature in the boundary layer, you can see that it has large-scale features at low Rayleigh numbers, low meaning 10 to the power 11. But as it progresses, it assumes smaller and smaller scales. Is same true is velocity field, and then here the shear stress field. And what is the important result? The Nusselt number plotted as a function of Rayleigh number you have these red circles from the present simulations, and these are from York-Schumacher simulations here for a different set of conditions. And if you fit the power law to this, you'll get about 0.33. Another way to see it is you normalize it by Rayleigh to the power 1/3 approximately, and you see it's flat there. So even if you go up to 10 power 15 or so, it doesn't seem like there is any tendency towards the so-called ultimate state. So basically, that's my closing remarks. A group has accumulated large and versatile numerical database for 3D Navier-Stokes turbulence. We can query essentially any desired property and evaluate existing or new theories, help build new ones. I just discussed 3 of them for you here. Thank you so much.
This area law, is it obvious that it's not dependent on the shape of the contour? Because, of course, the circulation for one particular contour is independent of its evolution. However, you average over different shapes of contours with the same R.
Yes.
And this absolutely
no. I have taken for those calculations squares all the time, only squares for getting these moments, etc.
Right.
Now, if you sometimes average squares and then sometimes rectangles, even though nominally they are about the same, you cannot do that. You don't know what error you introduce by doing that.
Okay.
It's all for only squares. Yeah, it seemed like that is the simplest thing to do, given that it is relatively insensitive. But as Sasha showed and Sasha Palikov showed, there is some dependence with respect to the aspect ratio, for instance. And so those things, I think, are essentially next order in the type of understanding one acquires.
In this large database, is any of it at all compressible, or is it all incompressible?
Yeah, there is compressible data as well. And there, what we find is, this was the root of the question I was asking this morning. If you separate the flow field into dilatational and divergence-free thing, then you actually find that the divergence-free part really follows pretty much like the standard incompressible case. I mean, one has to be a little bit careful. If the, but okay, I mean, qualitatively, my statement is correct. Yeah.
Thank you.
I want to comment.
You want to turn this on?
Oh, yeah. I want to comment about this comment about Sasha Palikov. We discussed that with him, and he pointed out that if you take Kolmogorov index and compute gamma square, then it's totally calculable through the pair correlation, and then of course it depends on the aspect ratio. And I explicitly computed that depends using Mathematica, and we compare that with data from Srini, it perfectly matches.
Yeah.
However, it depends on the index. If index is 1/2, like I predict, then it is exactly area and does not depend on aspect ratio.
In fact, I would say the basis for Sasha's expectation that it is half is really the independence of the expected properties on the aspect ratio. So half is, as he said, exactly independent of aspect ratio and everything. But we don't exactly know whether it's half or not. It's an asymptotic result, as he says. We don't know whether we have reached what is asymptotic. Unless you have finite Reynolds number correction, you cannot really say very much about it. But the direction seems to be, as he showed earlier, in the right way. It's a very interesting result, actually. Yeah.
Hi there. So you presented these Rayleigh-Bernard convection simulations up to Rayleigh 10 to the 15, getting Rayleigh to the 1/3 power.
Yeah.
Could you speculate on some of the other work which seems to suggest a transition at similar Rayleigh numbers, and where the discrepancies might arise?
I sort of went through this very fast. the people who have tried to anticipate this, they have only very few data points towards the end of their experiment or simulations. And you can fit probably using 2 or 3 points, whatever power law you like. I'm not being very unkind because this has been pointed out by others, especially Charlie Doring. Another thing is that in experiments, when you push the Rayleigh number, which I know very well, many of the boostness characteristics are lost usually. Because either the Prandtl number becomes unclear, or, the temperature at the middle of the layer is not exactly equal to the mean of the two, all these kinds of things. And that's the reason we actually went to simulations where you can control the boostness characteristics and so on. I mean, there are limitations to our own results as well, which I have sort of hidden from your eyesight for now. But the point is that at least for this case, which we have computed, there is no tendency towards any ultimate scaling. It doesn't follow that if we computed up to 10 to the power 20, it will not be. But at least there is one instance where within the Rayleigh number range covered in experiments that claim to have seen transition, we don't.